Hey everyone, and welcome. Are you ready to finally get the hang of spherical lenses? Well, you're in the right place. This explainer is made just for you, the Class 10 students, to help you absolutely crush it in your exams. Today, we're going to break down everything you need to know, making it super simple and easy to remember.
So, what's on the agenda today? Here's our game plan. First, we'll get to know the two main types of lenses. Then, and this is a big one, we'll learn how to draw those all-important ray diagrams. After that, we'll nail down the sign convention rules, put the lens formula to work, and finally, we'll see how this all connects to real-world things like eyeglass prescriptions. Let's get started.
Okay, first things first. Before we can do anything else, we have to get to know the two heroes of this chapter, the two main types of spherical lenses we'll be working with.
And here they are. This slide lays it out perfectly. On the left, you've got the convex lens. See how it's fat in the middle? That shape makes it bring light rays together, which is why we also call it a converging lens. Now look at the concave lens. It's the total opposite. Thinner in the middle, thicker on the edges. It spreads light out, so we call it a diverging lens. Easy, right? And this is what they actually do with light. It's pretty cool to see. Look at the convex lens. All those parallel light rays come in and bam! They get focused or converged to a single point. Now see what happens with the concave lens. The light rays hit it and spread out, or diverge, as if they're coming from some imaginary point behind the lens. This is the one fundamental thing you need to remember about each lens.
All right, now for what might be the most important skill for your exams, drawing perfect ray diagrams. Seriously, getting this right is all about knowing 3 simple rules. And please, please, please always remember to draw your arrows to show which way the light is going. It's such a tiny detail, but it makes a huge difference.
Rule number 1 is your best friend. It's about a ray that comes in parallel to the principal axis, that main horizontal line. If it hits a convex lens, it's always going to bend and pass through the principal focus on the other side. For a concave lens, it bends outward. But if you trace that ray backwards, it'll line up perfectly with the focus on the same side. This is the most useful rule for sure.
Now, rule number 2 is literally the exact opposite of the first one. It's like hitting rewind. If a ray first goes through the principal focus before it hits a convex lens, it will come out perfectly straight, parallel to the axis. And for a concave lens, if a ray is aiming for the focus on the other side, it will also come out parallel. See? It's just a reverse path.
And here's the easiest one of all. This one's a gift. Any ray of light that passes right through the optical center, that's the dead center point of the lens, it just goes straight through without bending at all. No deviation, nothing. It's a straight line. Just by drawing any 2 of these 3 rays, you'll find exactly where your image is formed.
Okay, drawing is one thing, but what about the math? To solve numerical problems, we need a set of rules for our plus and minus signs. Think of these as the traffic laws of physics. We're going to use what's called the new Cartesian sign convention.
Don't let this list scare you. It's actually super simple. Think of it like a graph in math class. The optical center is your origin, 0, 0. Anything to the right is positive, anything to the left is negative. Anything above the axis is positive, anything below is negative. But here's the part you absolutely have to burn into your memory. The focal length, f. For a convex, converging lens, f is always positive. For a concave, diverging lens, f is always negative. Get that right, and you're golden.
All right, deep breath. We've got the rules for drawing, and we've got the rules for signs. Now let's put it all together and actually solve a problem that you might see in your exam. And this is the magic formula you need, the lens formula. It's this beautiful little equation that connects u, the object's distance, v, the image's distance, and f, the focal length. Now pay close attention to that minus sign. It's 1 by v minus 1 by u. The mirror formula has a plus, so don't mix them up.
Okay, we're going to break down example 9.4 from your textbook. So an object that's 2 centimeters tall is placed 15 centimeters away from a convex lens with a 10 centimeter focal length. Let's list what we know, using our sign rules. Object height, h, is upright, so it's plus 2. It's a convex lens, so the focal length f is positive, plus 10. The object is on the left, so object distance u is negative, negative 15. Our job, find v and the new height h prime.
So first, let's rearrange our formula to get 1 over v by itself. That gives us 1 over v equals 1 over f plus 1 over u. Now we just plug in the numbers, being really careful with the signs. So that's 1 over positive 10 plus 1 over negative 15. We do a little bit of math with the fractions, and we get 1 over 30.
So if 1 over v is 1 over 30, that's easy. V must be plus 30 centimeters. Great. But what does that little plus sign actually mean? Well, remember our rules? A positive distance means it's on the right side of the lens. And when an image forms on the opposite side of the lens from the object, it means the image is real.
Okay, we know where the image is, but what about its size? Is it bigger, smaller, the same? For that, we need the magnification formula. Magnification, or M, is just the image height divided by the object height, and it's also equal to V divided by U.
So let's calculate it. Magnification M is V over U, which is plus 30 divided by negative 15. That gives us negative 2. Now, what does this negative 2 tell us? Well, the 2 means the image is twice as big as the object. And that minus sign, that's our clue that the image is inverted or upside down. To get the final height, we just multiply the original height, plus 2 centimeters, by our magnification, negative 2, and we get negative 4.0 centimeters. So, the full story is, we have a real, inverted, and enlarged image.
Okay, last section. Let's connect all of this physics to something you've definitely seen in the real world, an eyeglass prescription. This is where the whole idea of the power of a lens comes into play.
Power is just a fancy word for how strong a lens is, how much it can bend light. If a lens has a short focal length, it bends light a lot, so it's very powerful. The formula is beautifully simple. Power, P, is just 1 divided by the focal length, F. But, and this is a big but, the focal length must be in meters for this formula to work. Don't forget that.
And the unit we measure power in is the diopter, which we write with a capital D. You've probably heard this word before, right? From an eye doctor? It's really simple. 1 diopter is just the power of a lens that has a focal length of exactly 1 meter.
And this right here is the key to understanding prescriptions. Just think about the signs. We already know a convex lens has a positive focal length, right? So its power will also be positive. A concave lens has a negative focal length, so its power will be negative. If your prescription says plus 2.5D, you've got a convex lens. If it says negative 1.0D, you've got a concave lens. Simple as that.
And that's pretty much it. But before you go, here's a little challenge for you. A lens has a power of positive 2.5 diopters. First question, is it converging or diverging? And second, can you figure out its focal length in centimeters? Just think about the sign and remember the formula. It's a perfect way to check if you've really mastered everything we covered today. Thanks for watching.